This conference will now be recorded.
Very good morning, students. So, NEET UG 2023 exam is just over. So, we'll just try to solve all the questions of the physics paper in some subsequent classes. So, here I think the title is little wrong over here. So, it will be just a minute. I'll correct it here. Okay, I think title I cannot change. Maybe this is not here, just this one. So we'll be solving all the questions from NEET UG paper 2023. So let us take the problems one by one. Okay, so we'll see this thing. All right, so the first problem we have taken here is the ratio of radius of gyration of a solid sphere of mass capital M and radius capital R about its own axis to the radius of gyration of the thin hollow sphere of same mass and same radius about its axis. So its axis and its own axis means the axis of symmetry. Okay, so what we have to find out? We have to find out the radius of gyration of a solid sphere which has got mass capital M and radius capital R, and also we have to find out the radius of gyration of a thin hollow sphere of same mass, that means mass capital M and radius capital R. Okay, so how do we calculate radius of gyration? Radius of gyration, if suppose K is the radius of gyration, okay, radius of gyration is just a distance from the axis of its rotation or its symmetry axis. It's a distance where the moment of inertia will be exactly equal to like it is defined in this way, that radius of gyration is a distance or it's a distance where the whole mass is considered to be concentrated and the moment of inertia of that object about its own axis will be mk square, if this k is the radius of gyration. Okay, and this is exactly equal to the moment of inertia of the original mass distribution. So radius of gyration is defined as the distance about which, if you calculate the moment of inertia uh, such that the mass, whole mass is concentrated at that particular point, then the moment of inertia about that about the axis at that particular point is exactly equal to the moment of inertia of the object with its original distribution of mass. Okay, So this is the formula. So if we want to find out radius of gyration, then k will be equal to square root of I over m. That means we have to find out moment of inertia. So that's the thing. So we have to actually calculate moment of inertia of the object. So here we have got solid sphere and thin hollow sphere. Let us first find out the moment of inertia of the solid sphere. So it is very easy. We'll do it here. The moment of inertia of a solid sphere can be calculated in this way. See, if this is a solid sphere in this figure, and this is axis of rotation, okay, axis of rotation. Now what we can see a solid sphere, a solid sphere, a solid sphere can be considered, to be composed of considered to be composed of a number of disks. Okay, number of disks, and you can say this disk has okay, so disk has actually varying radius. Okay, number of disks of varying ready. Okay, that I'll explain how it is. See, so a solid sphere can be considered as composed of thick disk. Thick disk means, see, you can see this disk. Disk has a certain thickness, not just a sheet. It has certain thickness as well. Okay, so let us consider to calculate moment of inertia of a solid sphere. See what ultimately we have to do, I'll tell you here. See, we have to find out moment of inertia of an elementary disk, and if we can take sum of the moment of inertia of that elementary disk for the whole sphere, then it will be done. Let us do it here. Let us consider a disk, okay, such a disk over here, and it is considered at a distance x from the center of the sphere, at a distance x, and it has got a thickness of dx. Okay, it has got a thickness of dx. Okay, this disk has got a thickness of dx. All right, so thickness of dx. So we have considered a disk, thick disk, at a distance x from the center, and the disk has got thickness dx. Now look, disk are like this, a circular body with certain thickness. Okay, with certain thickness, and you know it has got masses all over here. It has got masses everywhere. Okay, everywhere it has got mass. So if we want to find out what is the volume of this disk, volume of the disk will be area, okay, area into thickness. This is how we can find out volume if we want. So in this case, look, in this case, this is the one, let us say this is y, this distance is the radius of the disk. If I know the radius of the disk, then finding out area will not be difficult job, and we know the thickness dx over here. And see this distance is r, this is radius, this is nothing but radius, this is like this is r. Then can we find out y? We can find out y in terms of x and r. Okay, we can use the Pythagoras theorem. So y square is equal to r square minus x square. So this we can keep somewhere. Okay, if we require we can use this. Okay, so what we have to do, we have to first of all find out the moment of inertia of this particular disk itself about its own axis, about its own axis. Okay, so here I think I should not take this as axis of rotation. According to my figure, this could be oil said axis of rotation. Axis of rotation, I should say this one, because we want to calculate axis of we want to calculate moment of inertia of the disk about its own axis, So we know from the result of moment of inertia of the disk, we know mr square by 2. Okay, mr square by 2. If the radius of the disk is r, then the moment of inertia of the disk about its own axis is mr square by 2. But in this case, we need to find out what is the mass. So since it is actually elementary disk, then I'll tell this is dm, mass is dm. Okay, mass is dm. Let us take small m itself, dm, and instead of r we have got here y, right? Y square, y is the radius here in the figure, given figure left hand. So this figure, see, radius of the disk is y and thickness is dx. Okay, thickness is dx. So this is dm into y square by 2. So this is the moment of inertia of the elementary disk. So moment of inertia of the elementary disk will be dm y square over 2. But what is dm? dm can be calculated as rho into dv. dv, what is dv? dv is the area of the disk, elementary disk. So what is rho? Rho is the total mass of the sphere divided by total volume of the sphere. Okay, this is the rho. And what is dv? dv is c pi y square into dx. This is dv. Okay, we'll put the value of y later. First of all, let us write over here. So what we got, dy. So moment of inertia of the elementary disk is m by, okay, 3m by 4 pi r cube. Okay, this, then pi into y square dx. Okay, pi into y square dx. This is one thing. And see again, this y is there, it is dm actually, then y square by 2 is also there, y square by 2. Now if we just simplify a bit, then see we get 3m by 8. See, this pi goes off, 8 r cube, and then y to the power 4, y to the power 4 dx. Okay, now look, I'll just erase some of this. I have got moment of inertia of the elementary disk. Now if I integrate it, so what is variable over here is the x, right? See, I have got radius here plus r and here minus r. If the x vary from, see, minus r to plus r, then all the disk will be covered, isn't it? I'm just writing here. You can just see, if I want to calculate the moment of inertia of the whole sphere, now look what I'll do. let me first complete this. 3m by 4 8 r cube, and y square is this. Y square is this. So r square minus x square is y square. So whole square of that will be y to the power 4. So then dy is this thing. Now if we want to calculate the moment of inertia of the whole sphere, then I have to integrate this dy in the limit r x is equal to minus r2 plus r, okay, to get the moment of inertia. So look, I'll write it here. 3m by 8 r cube, r cube, all others are variable. I'll write it here. X is equal to minus r2 plus r, and this is r square minus x square whole square dx. Okay, now look, I'll just erase all this. I'll erase all this because we have already learned these things. Now see, I'll just simplify a bit this one. So 3m by 8 r cube, then minus r to plus r. This is r to the power 4 minus 2 r square x square plus x to the power 4, right? And we have to integrate over dx. Then this will be 3m by 8 r cube as it is, r to the power 4 x minus r2 plus r. Okay, here minus 2 r square, then x cube by 3, here also minus r2 plus r, then it is x to the power 5 by 5 minus r2 plus r. So these are the limit. So if you simplify it, what you are going to get is, see, you'll get, see here, this is the upper limit, this is the lower limit. So you'll get here 2 r to the power 5, then here you'll get 4 by 3 r to the power 5, and here you'll get again 2 by 5 r to the power 5. Now look, this factor is again multiplied, 3m by 8 r cube. Okay, so if we take this r to the power 5 common, then it will be 3m by 8 into r square, and along with that multiplied, see 2, this is 5, so you'll see there will be 15. So this will be 10 minus 5 plus 6 plus 6. No, somewhere some mistake. So this is 2 by 5, right? This 6, 15. Okay, this is actually nothing is there. This will be 13, I guess. So 30, I think 30, 25, no. Okay, it is actually all the calculations are fine so far. We'll just do this simplification. Because of space, I am just scribbling. Here, look, if this is actually becoming 3m r square by 8, and here you have 2, okay, then 4 by 3 plus 2 over 5. This is the one. So in this case, you look, this will give you 2 by 3 and 2 by 5. So 2 by 3 plus 2 by 5. So this is 10 6 by, so 16 by 5, sorry, 16 by 15. So it will be 16 by 15. Okay, so 3 mr square by 8 into 16 by 15. That means 3 by 5, and this is 8 to 6. So 2 by 5. So we have seen that moment of inertia of the solid sphere is will be 2 by 5 mr square. If you had known this result itself, then you need not do all those calculations for solving this problem. Generally, you should remember this some of these values. So 2 by 5 about its own axis, it will be 2 by 5 mr square. This is known for you, I hope. So moment of inertia. So moment of inertia equal to mk square. So we have got 2 by 5 mr square. So k will be how much? Square root of 2 by 5 here r. Okay, so this is one. Now let us go to, this is hollow sphere. Okay, it is a hollow sphere. So look here in this hollow sphere, this is solid sphere. Everywhere there was mass, everywhere mass was there. This was solid sphere. Okay, solid sphere. There was mass everywhere. Okay, this is solid sphere. Everywhere there was mass. That's why we had to calculate disk. But see, in case of thin uh, sphere, what we can do, we can uh, think of a ring. Okay, we can think of a ring. Okay, or a cell. We can say thin, thick cell, not thin. Anyway, so we can just consider the ring, or uh, okay. So look here. Let us consider this kind of ring, or this is called stripe also. Let us consider stripe or ring. It will be actually, see how it will be. It will be having masses. Oh, sorry. Masses not everywhere. It will be having masses. It is kind of ring actually. Okay, kind of ring, but it is kind of thick ring. Okay, it has masses. It has two radius, you can say, two radii. So it does not have mass here, no mass here. Only mass is there on the periphery, right? So we consider such a thing over here, and let us say this angle is theta, and these are anyway r, and this angle, this small angle is d theta. Okay, d theta. So this thickness, this is the thickness, you can see this thickness, or this thickness, this is r d theta. Okay, this is r d theta, r d theta. Okay, r d theta. And see, this ring has got uh, the ring has got its radius. Ring has got a radius. See, this will be the radius then, and this is, see, this will be r sine theta, r sine theta. Okay, and at how much distance it is from the center? It is at a distance r cos theta. Okay, at a distance r cos theta. So it is so what we will do, we'll calculate the moment of, say, moment of inertia of a ring about its own axis is mr square, mr square. Okay, all right. So moment of inertia of a ring moment of inertia of a ring about its own axis is mr square. So keeping that in mind, if I say this has got this elementary ring, let us say ring itself, elementary ring has radius r sine theta. Okay, I should not take any variation in this way because this variation will be taken care by theta. Okay, along this direction. Okay, I have taken this one as one ring. I would have taken one more here, one more here. Okay, one more, another more here, right? So I have to first take this elementary ring, then I have to do all the calculations for this particular one, as we have done in case of elementary disk in the solid sphere. So then we'll just integrate it. Okay, so elementary ring has got radius r sine theta, and ring has thickness. It is actually not exactly like a thin ring. It has got some thickness, r d theta. Okay, r d theta. So you know, it has it has volume. It has volume since it is thick ring. So volume dv will be written as 2 pi 2 pi r 2 pi r. I should not say this is volume. I think I should say this as elementary area. Okay, area. This is yes, this is elementary area because mass is not there in the volume. So this is nothing to do with the volume. So 2 pi r sine theta. This is the perimeter into the thickness r d theta. So this is the this is the uh, area, elementary area. Okay, elementary area. And what is the mass? See, I need to find out mass per unit area of the given sphere, that is this m by 4 pi r square. So this is mass per unit area, mass per unit area. Okay, mass per unit area. So once we write mass per unit area and multiply it with this elementary area of the ring considered over here, then we will get the elementary mass of the ring. So this is sigma into dA. Okay, what is that? Then m by 4 pi r square, 4 pi r square into see 2 pi r square sine theta and d theta, which we may little bit simplify by this, and this will be half. So m by 2 sine theta d theta basically. Okay, so far what we have got dm. Now if we want to find out what is the elementary uh, moment of inertia of the elementary ring, then see, we know for a ring it is m into r square. So dm into r square is here r sine theta whole square. So this will be the moment of inertia of this particular ring. Okay, let me just write it here. So dm is m by 2. This is r square, and there was another sine theta over here, and here sine square theta. So ultimately it is sine cube theta, and obviously there was a d theta. So this will be d theta. Okay, so guys, what I'll do, because of lack of space, I'll just erase this portion little bit. We have got di. Now the job is to just integrate it over theta, and see how to take the limit of theta. That is also very interesting. I'll let you know how to do that. See, I have considered the theta with this particular horizontal, and this is r, actually this is radius. So if this radius goes on like this, and like this, finally when, see, radius will be here, all my ring will be covered like this. Okay, all my rings will be covered like this. All the, see, it can be considered to be made of a large number of thick ring. So here, if we vary the theta, then number of rings will be varying. Okay, so to calculate the moment of inertia of all, like of this holosphere, we have to sum of the moment of inertia of all such elementary rings. So how to do that? We can do the integration over di, and see, we are just integrating over theta. Theta goes from 0 to pi. See, 0 to pi, here it is 0, here it is theta is equal to 0, and at this particular position theta is equal to pi. So if this radius just rotate from 0 to r, then the whole sphere is covered. Okay, so that's how we will be able to integrate it. This is pi, and this is, say, di is m by 2 r square, and this is sine cube theta. Sine cube theta. Now it is, see, how to calculate sine cube, integration sine cube the theta. Okay, so how do you do that? So it is not very tough to do. Okay, what we can do, we can either we can either we can either remember, see, keep this sine 3 theta, this formula sine 3 theta is equal to 4 sine cube theta. So yes, sine 3 theta is equal to 3 sine theta minus 4 sine cube theta. So this formula we can remember. See, 4 sine cube, see, here we can multiply 4, so m by 8 r square 0 to pi, so here it will be 4 sine cube theta. Okay, d theta. So once we use this, what we can write using this identity, we'll just write this identity over here and try to do the integration part. So here m by 8 r square 0 to pi, 4 sine cube theta means 4 sine cube theta, it will be actually 3 sine theta, 3 sine theta minus of that, so 3 sine theta minus sine 3 theta, sine 3 theta. Now put it here, 3 sine theta minus sine 3 theta d theta. Now it is easy to do the integration part. Okay, so integration, see, 3 will be as it is, and sine theta cos theta will come, there will be minus sign coming up here, cos of theta, and say 0 to pi here, then minus here, cos, again minus will come, so plus, this is 3 theta divided by 3, and 0 to pi. This, if we use the limits or put the limit properly and find the values, see, cos of theta, cos of 0 degree is 1, and this is minus 1. Okay, then see, this is minus 3, and this will be impact -2 here plus 1/3, and here it will be again 2. Okay, so what we get, obviously there will be minus sign here. Cos of pi means -1, 3 pi means pi, -1 minus of this, so there will be -1 here, -2 here. So mr square by 8, this is 6 minus 2 by 3, so this will be mr square by 8, this is 16 by 3, so this will be ultimately 2 by 3. See, I have mentioned already, it is better to remember few results like this so that you don't have to do this many calculations and find out the moment of inertia of the hollow sphere. So what we have found out, the moment of inertia of hollow sphere IHS is equal to 2 by 3 m r square. Okay, all right, so look here, for a hollow sphere, this is solid sphere. Then for hollow sphere, it will be I by m. So I is here 2 by 3 m r square. So r will be here. Okay. Now see if we take the limit, ratio, this over HS is, see, this is 2 by, okay, let me write 2 by 5, and here 3 by 2. So this will be square root of 3 by 5. Okay, but here in the options nothing is given here, uh, so we can just think that this is root 3 by root 5. So this question was not like an option, so I am not given correct. So you may get some bonus marks for this. Okay, if you have attempted or not attempted, you may get some bonus marks over here. Okay, we'll go to the next problem. The next problem is here related to photoelectric effect. Let us see the work function of cesium, potassium, and sodium are, say, let us write work function is 5 for cesium, it is 2.14 electron volt. Work function 5, that is for potassium, is given as 2.30 electron volt, and 5 for sodium Na, that is 2.75 electron volt. Now incident electromagnetic radiation has incident energy 2.20. So incident energy, that means E, we know Einstein's equation of photoelectric effect is given by h nu minus, kinetic energy, maximum kinetic energy, this max of photoelectron, emitted photoelectron will be E incident energy minus 5. Okay, 5. At least to have photoelectric effect, E must be less, greater or equals to incident. Let us say this is EI. So incident electromagnetic radiation must be having energy greater or equals to 5. Okay, 5 means work function here. See, incident radiation has, see, EI has got a value 2.20 eV. So any metal surfaces which has work function below or equal to this will emit photoelectrons. So question was, which of these photosensitive surfaces may emit photoelectron? So it is the cesium which has less work function than the incident energy. incident energy of the photon or electromagnetic radiation. Okay, so cesium only. So the option D will be the correct answer here. So this question is the amount of the energy required to form a soap bubble of radius 2 centimeter 2 centimeter of a soap from a soap solution is nearly where the surface tension of the soap solution is given. See, if I have got a spherical soap bubble, it has got two surfaces. Okay, surfaces. That means it has got surface tension 2s. If s is the surface tension, okay, for a single surface. So soap bubble has got surface tension s. So I have to consider for two surfaces here. Okay. So see, first of all, since this, see, atmospheric pressure is there and there is some pressure inside, so there will be some excess pressure, and obviously atmosphere is acting or doing certain work against this excess pressure. So due to that, there will be some energy stored, or yeah, some energy is required. Okay, so what is that energy to form this bubble? So that is called surface energy, and surface energy is nothing but surface tension surface tension surface tension into surface area surface area surface area. See, here there are two surfaces. In case of soap bubble, you know that. So surface tension is given as 0.02 and sorry 0.03 newton per meter, and surface area, if the radius is 2 centimeter, then I can write pi r square is 2 into 10 to the power minus 2 meter whole square, pi r square. So this is the area. Oh, I'm sorry. So bubble, this is a spherical one. So 4 pi r square I say. So 4 pi r square is the area of single surface, but we have got two surfaces. So this is the thing we have to do. And if we just do this calculation, so let us say this is 3, this is 4, this is 2, and here 3.14 in place of pi, and again here I have got 4 from this square, and see here 10 to the power minus 2 from here and 10 to the power minus 4 from here, so 10 to the power minus 7 here. Okay, so if we multiply this, see 4 4 16, so this is 32 96, so 96 into 3.14, so and here, so I'm sorry, I think we have done some small mistake in the calculation part. So anyway, if you calculate this, how much you should get? See, you would get something if you multiply this, all the things properly. So you should get 310.4 into 10 to the power minus 7. So this can be written as 3.01. Okay, 3.01 3.01 this will be actually 10 to the power minus 6, which is 4 and 2. So 10 to the power minus 6. So this will give you 10 to the power minus 4. Minus 4 joule. This will be in joule. So look, this option B would be the answer for this question. Okay. So only thing is that you have to do the calculation properly. Now let us see resistance of the carbon resistor determined from excuse me, color code is given by this. See, 5% of 5% of tolerance is for gold. This is fine. Now the color of the third band. See, generally there will be color band, minimum 3 color bands will be there, maximum 4 color bands will be there. Okay. So the first, second, third, and fourth, like this. So here, if you remember this rhyme, BB Roy goes to Bombay via gateway. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 0 black, this is brown 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9. These are the corresponding color code. Now see first two colors. If I say this is first, this is second, this is third. So first two color actually goes with this goes with the number. Okay, first two digit. So here actually 2 2. So 2 2 means it will go with red 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 red. Okay, 2 2, and the third color will third number will go to the power as decimal place. So this will be 10 to the power. See, so 10 to the power 3. Third has got orange because there are 1000. So it should be 10 to the power 3. So 22 2 2 red red, and see this has to be 10 to the power 3. So 10 to the power 3. That means this orange will be the third band. So this is orange, such that you get 10 to the power 3. Okay, and the fourth one will be gold. Okay, I have got then red, orange, and gold. This is the combination color combination of this register, carbon register. So here it will be orange. Third band will be orange. I'll take up one more question, then I'll stop. So there are many more questions on this, like for this paper. We'll take up in the next classes as well. So here in series LCR circuit, LCR circuit. Okay, suppose there is a sinusoidal voltage applied to this. So L, C, and R. So L has got 10 millihenry, C is 1 microfarad, and R is 100 ohm. The frequency at which resonance occurs. So resonance frequency, you should remember, resonance frequency FR is equal to 1 by 2 pi root over LC. This is actually the resonance frequency. So how to find out the value for this? See, let us find out what is root over L. So L is 10 millihenry. That means this, and C is actually 1 microfarad. So this will be 9. So at 10 to the power 8. So this will be 10 to the power 4. So 10 to the power 4 is fine. Now we have to check what is this factor. Okay, this is 0.5 divided by 3.14. This factor we have to now see. So actually this can be made like this, and then do the division part. So how to do that? So we have got resonance frequency. So if we do the division, we'll get actually something like, see, okay, let me show you here. So this is 1 means this. So this I have got. So we have 314 again. So 1 point. See if I just multiply, sorry, take point over here. So 0 will come here. So it will be something like 5. So like this, and this will go with, it will go with 9. Okay, it will go with 9. So 1.59 into 10 to the power 4, that means I can write 15.9 into 10 to the power 3, and this is kilo, so this is hertz. So 15.9 kilohertz will be the right answer for this question. Okay, 15.9 kilohertz. So thus we have solved few questions from this Neet UG paper. So this is not the correct title. So today we are solving uh, Neet UG paper 2023. So let us stop it here. We'll take up other questions in the subsequent classes. So thank you for your patience. Bye for today.